Hello there. Welcome to another biology podcast. Hope this podcast finds you well. And today we're talking all about designing primers for PCR. And this is specifically to help those students that are working on Mr. Clay 13biology.wikispaces.com and engaging in a primer design activity. So without further ado, let's get into some biology. This podcast is particularly focused for those people that are working on Mr. Clay 13biology.wikispaces.com and are doing one of the primer design projects on there. So I hope by now those people that are watching this that are doing that have received their data and are ready to make some progress. The objective of this podcast is actually to help you refine a big long list of possible microsatellites and identify the ones that are most suitable for using in a PCR reaction. And in order to refine a big long list of microsatellites, I'm going to discuss a few criteria, in fact 6 criteria, that you can use to reduce that list down. But before we talk about any of the criteria, let's just have a quick look at the data and what it's all about. So on your screen right now you should see an Excel spreadsheet that looks a little bit familiar to you. Let's have a quick look at what it all means. Each of these rows represents a microsatellite that the software we used has selected. And now we've got to filter through this and figure out which are the best. On here, I'm not going to bother going all the way down to the bottom, but there are 152 in this particular sample. So, like I said, each row represents a different microsatellite. And on the first column, we've got a code for each particular one, so that it's easy for us to communicate about what microsatellite we're talking about. The software has also designed a primer for each, or 2 primers for each microsatellite. Obviously, in PCR, each particular area that you want to amplify needs 2 primers, one at the forward end and one at the reverse end, or one on each strand, if you like. And here's the first primer for this particular microsatellite that's been designed, and there's the second primer. So we've got primer left and primer right. We've also got some other pieces of information. We've got what we call the TM of this particular primer. So the primer left has a TM of 60.223. We'll talk about what TM means in a little while. We've also, we can find out here that it's got a GC percentage. We'll talk about that again in a little while. That's the 55% of this is made up of G's or C's. And we don't need to worry about the left start and the right start. But here we've got the same thing for the other primer that's involved in this particular microsatellite. And we've got again the TM and the GC percentage. That's going to be really important when we're actually trying to narrow this list down to just the primers that are actually going to be useful for our profiling. So what you've seen there is we've got a list of potential microsatellite regions that could be really good for our DNA profiling. There may be hundreds. In our example that we've just seen, there was 151 different microsatellites to choose from. But not all of those will be any use to us at all, so we need to actually refine that list down to the microsatellites that will actually be useful in our profiling. And to do that, what we do is we screen the potential microsatellites against a set of criteria to find out which ones will be useful and which ones won't. So we'll eliminate them basically if they're not matching the criteria that we want. And we're going to use 6 criteria by which to refine the microsatellite regions that we've got. So let's have a look at them in turn. The first one is the length of the primer. And as it says on the screen there, the primers should be between 18 and 30 bases in length. So when we're looking at any particular microsatellite and judging it for its suitability, one of the first things we need to do is actually to look, is it the right length? So we've obviously got 2 primers for each microsatellite. And we basically count the number of bases in each of those primers, and if either of those primers have less than 18 bases or more than 30 bases, then we'll basically eliminate it straight away. Now on the screen right now, you'll see that we've got a primer there, and you can see the code on the left-hand side, and then you've got the first primer for that microsatellite. And it's going C, A, C, G, T, and so on. Now, if you actually counted those up, you'd see that it was only 17 bases long, which means that we can eliminate that microsatellite straight away because the primer for that particular microsatellite, or at least one of the primers for that microsatellite, isn't of the right length. So we need to check all the microsatellite areas, or all the microsatellite regions that we've got, and check to see if the primers that we've got for those microsatellites are the right length, and then eliminate the ones that aren't. Now the second criteria we're going to use is what we call the primer melting temperature. And as shown on your screen there, it's also like abbreviated to TM, and you can see the M sort of in sort of a subcase there. Now let me start by actually explaining what the primer melting temperature actually is. Now, as you know, or you should know by now, that during PCR, the first stage is actually what we call denaturing or denaturation, where the temperature is increased, and that causes the double-stranded piece of DNA to separate into two single-stranded pieces of DNA. And the diagram on your screen sort of shows that as the temperature increases, the likelihood of the DNA double strand actually separating into two single-stranded pieces also increases. So the higher the temperature, the more likely it is to split up. Now, what's interesting about DNA is there's not one temperature that all DNA denatures at. So there's not one temperature that will allow all double-stranded pieces of DNA to actually separate into the single strands. And there are actually another number of different things that actually affect how much heat is required to separate DNA. For example, how many G's and C's are present. If you look at your screen right now, you'll see that you've got a diagram of DNA there, which I'm sure you're familiar with, and you can see the bases in the middle. Just have a quick look. What do you notice the difference between G and C and where A and T are bonded together? I'm hoping you can see that between C and G bases there are 3 hydrogen bonds compared to only 2 between A and T. So if you've got a piece of DNA that's got a high proportion or high concentration of C or G bases, then you're going to have more hydrogen bonds for that particular strand of DNA, and it's going to require more heat or more energy to actually separate them. Which means the primer melting temperature is actually increased. So very simply, the primer melting temperature is actually the temperature that's required to separate the two pieces of DNA where the primer is actually going to bind. Now the important thing for you to remember is that primers should have a TM of between 55 degrees C and 72 degrees C. So once again, you go through the microsatellites that we've got, you check the TMs for each of the primers for each microsatellite, and if any primer has a TM of under 55 or over 72 degrees C, then you can immediately eliminate that microsatellite from your search. Okay, so now on to the third of the criteria. And this is what we call the TM difference, or at least that's what I've called it. So by now we should be familiar with this idea that for each microsatellite there are 2 primers. And each primer has its own melting temperature, or TM. Now the third criteria dictates that the TM, or melting temperature, for each of the primers for one microsatellite should be within 5 degrees of one another. And if you look on your screen right now, you'll see we've got a couple of rows from the spreadsheet there, and the bottom row that's highlighted with the 2 cells in yellow, you can see you've got a left TM, that's the melting temperature for the left primer, and you've got a right TM, which is the melting temperature for the right primer, and you can see that there's a difference there of over 7. So because there's more than 5 degrees difference between the 2 melting temperatures for those 2 primers, then we would eliminate that microsatellite. Okay, so moving on to the next criteria, number 4, we've got GC concentration. Basically, this criteria dictates that all primers should have a GC concentration between 40 and 60%. That basically means that over the course of the primer there shouldn't be less than 40% of the primer made up of G and C, but there shouldn't also be more than 60% made up of G and C. Or guanine and cytosine if you want the full term for the name of the base. So looking at the data on the screen right now, we can see we've got some we've got the left-hand column there is the left GC percentage, and the right-hand column the right GC percentage, and we would basically use that information to identify if we've got any primers that had a GC percentage of less than 40 or more than 60. And right now you can see, if we just look there, second from the bottom on the left-hand side, the left GC percentage for one of those is 61.111. So following the criteria, we would eliminate that microsatellite. Okay, so on to number 5. Of course, if you're struggling to keep up here, remember you can pause and rewind and go back and watch it again. But we'll move on right now to number 5, which is called contiguous bases. And basically this is talking about not having one specific base repeated more than sort of 3 more than 3 times in a row. So primers should never have a base repeated 4 or more times in a row. So we should never have a situation where we've got, say for example, A. The maximum number of A's in a row should be 3. And looking at the data here, we can see we've got a bit of a problem with the second microsatellite down, and the one that's VHK on its code. You can see that the primer there has got 4 T's in a row. The first 4 bases in that primer are 4 T's, which would mean we would eliminate that microsatellite from our list. Okay, so now our list is getting much smaller, our list of microsatellites that we could potentially use. But onto the final 6th criteria, we've got GC repeats at the 3' end of the primer. So let me explain what that actually means. So I'm hoping you remember that DNA has a 3' end and a 5' end, or at least the strands of DNA have a 3' end and a 5' end. And that's obviously the same for primers, because the primers are actually made of DNA. So what this is saying is that primers should never have more than 2 G's or C bases within the last 5 bases at their 3' end. Now if you look at your screen now, you'll see that there's basically that's a primer that's actually written on the screen there. And it reads from 5 to 3, which is exactly the same as all the data in the spreadsheet that you're looking at. So when you see the primer written down, it's actually going from the 5 end to the 3 end. And this criteria is really concerned with the 3 end of the primer and ensuring that there's not more than 2 C's or 2 G's at any 3' end of a primer. So the primer on your screen there, you can see it's got 3 G's bases within that last 5 bases at the 3 end. So without a doubt, we would eliminate this microsatellite from our list of possibles. So they're the 6 criteria that you're going to use to actually refine that list of primers down so that we can make sure that we only use the best microsatellite regions for our DNA profiling. Okay, so obviously the data that you've been given, or you're going to be given, is going to be in the form of an Excel spreadsheet, and there's a good reason for that. Obviously Excel is a piece of software that allows us to handle lots of data efficiently and accurately, and that's exactly what we want you to do here. So to be honest, you could go through all 150 or 900 or however many primers or microsatellites you've got to choose from. You could go through each one of them manually, searching through, counting the number of repeated bases and identifying the numbers that are over 40 or under 60, whatever. But basically the point of actually putting them on an Excel spreadsheet is so that you actually use the software to be more efficient and more accurate, just like scientists are in the real world. So I've got the spreadsheet here on the screen that you can see, and just for example, one simple way that you might want to do it is to use formulas. And now I'm not going to actually show you any specific formulas, because I think that's part of the challenge of actually figuring out how you can use this software innovatively to solve the problem. But just to sort of give you a bit of an idea, I could just click insert here, and I could decide to put another column in, which is going to put another column just there to the left. And then if I want to, I could just press equals, and then I'll find a formula somewhere that allows me to count the number of G's in this this thing here, or search this for 4 G's or 4 C's or 3 C's or 3 G's or 4 A's or whatever, just to find out if I've got any contiguous bases or if I've got more than 3 G's or 3 C's in a row, etc., so that I can make sure that I'm really accurate about the primers that I eliminate, and also really efficient rather than have to count them through. And you could do that with pretty much all of those criteria as well. Think of how you can use Excel to screen the data for you so you can identify whether you've got the right primers or not really accurately. Okay then, so there's some tips on refining your primers. I hope that helps you with your private primer project that you're working on. And if you need any more help, then I'm sure you know by now that you can post questions on the wiki space, and other people will pick those up, including myself from time to time, and hopefully you'll be able to get some help that way. In the meantime, good luck with your project. I hope this was helpful, and as always, keep it real.